Hello everyone, welcome back to COP-3402. Today we're going to be reviewing for the midterm exam. So on the schedule page, or schedule section I should say, of the course homepage, you will see the exam is scheduled for March 3rd. This is going to be in the normal classroom that we have class at, so that's going to be CB2 207 right here at our normal time, so 12 o'clock. So you'll have the full 75 minutes to take the exam. And as for what's going to be on it, let's click on this link. There will be a total of 20 questions. There are going to be 13 multiple choice questions and 6 short answer questions, which are each going to be worth 1 point. And then a long answer question that will be worth 5 points. So the multiple choice questions are your standard multiple choice questions. A, B, C, and D will be the options. The short answer questions will be short, definitely short, more like multiple choice without the multiple choice options given to you. And the long answer will be asking you to write a comprehensive computer program, a not too long, but comprehensive in the sense that it will involve using many of the pieces of system software, many of the syscalls you've learned so far in the semester to construct one program. Now, what I want to spend the majority of this lecture on is just reviewing what topics will be on the exam. So let's start from the top here. In terms of file systems, first we're going to ask in this review, what makes the Unix file system hierarchical? So let's take a look at a diagram here where I can draw this out. What makes it hierarchical is the fact that files can be directories and directories can contain other directories. So there's a few different ways to visualize this. One way is to view each file, each directory I should say, as a table mapping file names to their inode numbers. So remember we had reviewed this previously. I'll make these lines a bit neater. Okay. So if we have a file, let's actually visualize this in 2 ways. So let's say we have our root directory here, slash, and underneath the root directory there are other files. So we can say, for instance, the user directory is a file, and the bin directory is a file. And really, well, bin is actually a symlink to user, so maybe I should draw this like this instead. The user directory contains the bin directory, and maybe underneath the root directory, there is the home directory, let's say. We'll say home. And maybe on my machine, because my name is Brent, there'll be a Brent directory under home for my user. And then maybe under my home directory, I have a file called todo.txt, something like that. So you can see pretty clearly here how these files and directory files form a hierarchical structure. And the way this would look in terms of inodes and how we represent these directories sort of more conceptually, you can think of them as just mappings between file names and their inode numbers. So for instance, the slash directory here, that would be its name. It would not have itself in the table. Let me put this over here so we can see that it's the name of the table, not the name of any of the files in this table. The user directory, let me actually move this line down here, delete these two. Let's say the user directory has an entry here and the home directory has an entry here. The inode numbers of these directory files might be like, I don't know, let's say 1, 2, 3, 4, and maybe home has an inode number of 5, 6, 7, 8. Let's just say. Maybe I'll label these table columns just for clarity. So we can say name and inode number. And so this is essentially what directory files are. They're just mappings of names to inode numbers. And we can see if we, by just having this sort of mapping exist, we can map names of other directories to inode numbers, and in doing so we can create Let me change this here so we can sort of see this hierarchical structure. So maybe this user directory has the bin directory, so we would put this here. Maps bin to, for instance, I don't know, 1337. I don't know if any of you like solving LeetCode problems. So you can kind of see immediately from this diagram how the hierarchical structure arises from this sort of mapping of directory names to unknown numbers. This really goes more like here, yeah. Okay, so I think that pretty comprehensively answers that first question, pretty fully answers it. So let's go on to the next one. What is the difference between absolute and relative paths? Well, absolute paths always start with the root. They are absolute in the sense that they always begin at the root of the file system and tell you the full path to your destination. So for instance, the path name here, /user, or maybe /home/brent/todo.txt. This would be the full absolute path to to2.txt. And relative paths, on the other hand, so I'll label this as absolute. Make that text blue so it sticks out. On the other hand, maybe I'll move this around to the left. Relative paths are relative to a current working directory. So maybe to make this clearer, I'll say assume cwd is /home, so the full path to the home directory. If we assume the current working directory is /home, then we can get a path to the same file here with just brent/todo.txt. This assumes the current working directory is /home/. So relative to a current directory. One cheat that I always like to use is just if the file path begins with a /, it's an absolute path. If it does not begin with a /, it is a relative path. Okay. How are parent directories referenced in the file system? Okay, this is a good question. There is something I've omitted from this diagram so far, and that is parent directories. So if I were to illustrate this, what I would have to add is another directory entry here to each of these nodes in this tree. That is, maybe you remember from the previous lecture, ... So ... always refers to the parent directory. So maybe I will draw another arrow here to represent this. If I were to look at the ... directory in the /user directory, if I were to try and cd into that directory, let's say, using the cd command, it would take me back to the home directory. And I'm going to open up my terminal now and actually demonstrate this. Well, there we go. I'll go to my root directory here. So I'm in my root directory, /, you can see my current working directory in my command line here. If I go into the user directory and then cd into ... you'll see I arrive back at the root directory. Now, as a special case, the parent directory of the root directory is just the root directory itself. So I'm going to write that in this diagram as well so you can see what I mean. This is like the only edge case with these parent directories. The rest are going to refer to the parents in this hierarchy. So draw this here, connect it back to the parent. So this is the one edge case. The parent directory of the root directory is the root itself. But in all other cases, I should say, the ... directory, or directory will refer to the parent directory. So draw that here as well, back to the user directory. Use a neater line for that. There we go. And it's going to be present in these two as well, so I'll draw that here, a little bit shorter. And in both these cases as well, the directory will point back to the parent directory will return back to the parent. So in the case of Brent, it will return to the home directory. In the case of home, it will return, oops, I drew this wrong. The home directory will return you back to the root directory. There we go, that's correct. And in the case of Brent, this will return you back to the home directory. Yeah, that's correct. All right, so I think we pretty fully answered this. The last two questions here, given a tree, which file is being referenced by a given path? well, there's different ways it could express these different paths, right? So for example, we had this absolute path to to-do.txt, and we also had a relative path to to-do.txt. One thing you should be able to do is look at different relative and absolute paths and identify which files they refer to in a file system hierarchy. So I might give you, for instance, on the exam, the current working directory and then a relative and absolute path, and ask you to tell me which file that those relative and absolute paths refer to, given that current working directory. And then drawing a file system tree, we've done that here. So there's also one more maybe special directory entry that I should mention. This is the dot directory. The dot directory just always refers to the current directory. So in case of the root, it'll be the same as dot dot. That's just because the dot dot directory entry for the root refers back to the root, but for every other directory entry here, if I were to add a dot, it would refer back to that same directory. So keep that one in mind as well. Okay, navigation. What is the working directory and how do you display it? So we've already discussed what the working directory is here in this diagram. The way you would display it, I'm going to split to my terminal window here, is with the Unix standard command pwd. So pwd just prints the current working directory. What is the Unix standard command to rename a file? Well, there is no specific command for renaming a file. So if I create a file here that we call hello.txt, and I wanted to rename it, what I would need to do is actually use the mv command, the move command, to move the file to the same location, so same place, but just giving it a new name. We can say goodbye.txt. And if I do this, you can see we have a file here now called, where is it? Right there, goodbye.txt. And the hello.txt file is gone because I had moved it, renamed it to goodbye.txt. What is tab completion? Tab completion is a context-sensitive mechanism on the shell that lets you press tab to automatically complete what you are typing. So if I'm typing, let's say, pw and press tab, my shell will automatically try to, well, tell me all the different options for completing pw, and you can see pwd is actually one of the options. There's also auto-completion for file names, so if I were to say cat, let's say open.c, so you can, there's a file here called open.c. If I were to just say cat and then start to type in open and press tab, I can automatically complete that to open.c. Note that this doesn't always work with all programs. I don't have any examples here right now, but some programs you might install may not have auto-completion set up for them. You have to set this up for each program, and a lot of programs provide that setup for you, but some of them don't automatically provide completions for you. And if you read the bash manual, it describes actually how to set up those completions for programs which do not provide it out of the box. Okay, so what Unix standard command will show you the text of a file? So we just saw this. This was cat. So again, I can say cat and then open.c and view the contents of this file. So cat stands for concatenate. That means that I can pass multiple files to this command. So open.c, read.c, and cat will print all of them in sequence with no breaks in between. What does grep do? Grep searches for a pattern within a given file or directory structure. So I can say grep main and then pass a file, open.c, and it will actually print out all the lines of the file that contain that pattern main. If I wanted to search in a whole directory structure, I could pass the -r flag to grep and the name of the pattern and just press enter, and it would tell me every file and line number, or lines I should say, that match the pattern main in my current directory hierarchy. And if you don't pass anything to grep, it will read from standard in. So I could say grep hello, and then I'll have to type in hello, and it will actually print it out to me because it matches. But if I said goodbye or just bye, it wouldn't print anything. And I can end the standard in input here by pressing Control D. How do you change the working directory to your home directory? So there's two different ways. The first way is to use the tilde. So we use cd to change our current working directory. cd, change directory. And we can use the tilde operator, not operator, symbol here I should say, to switch to our current directory. This is cool, but we might want to use the home shell variable instead. This does the same thing. So if I were to switch to a different directory here, desktop let's say, and then cd home, this would also work. The difference is that in bash, if you are going to type in a string, so if I were to say echo tilde and echo this out, it only expands to the string. And then if I instead were to type in echo home in double quoted strings here, which enables bash to expand variables within them, and then press enter, you can see that the full path gets expanded. So this usually isn't a big deal, but in some cases when you're running bash scripts or passing commands to programs, it can lead to unexpected behavior if you pass the tilde. In general, you want to use $home for passing commands to scripts. But on the command line, it's pretty useful to just use cd tilde. The Unix command to delete a file. Well, we just use rm. So we can use rm to delete a file. So if I go back to the directory I prepared for this lecture, desktop, midterm review, and I touch, let's say, a file hello.c or hello.txt, I can use the rm command to remove that file. If I try to remove it and it doesn't exist, I get a warning. To suppress that warning, I can say hello.txt, remove, -f hello.txt. -f is for force. And then I go get a warning message even if it doesn't exist. Now to delete a directory file, so I'm going to use the makedir command to create a directory here. I'll call it test. I can use rmdir to remove a directory that is not empty, and that will work. But if I make a directory here, test, and then create a file in it, test hello.txt, and try to run rmdir on that directory now, we'll get an error because rmdir only works in empty directories. So the way to delete empty directories is to use the recursive flags. You could say rm-f test, and this would actually recursively remove everything in that directory, including its files that it points to or contains. How does the implementation of deleting a file work? Does it remove the file's contents from the storage medium? No, it does not actually perform a write to disk, at least not for the file's contents. It just deletes the directory entry from the directory that contains the file. So, for instance, if I deleted my, I shouldn't do this, but if I were to delete my home directory here, let's say I just deleted the home directory and everything within it, all that would do is delete the home directory, the directory entry in my slash directory here. And that frees up the space for other programs to, the memory on my disk, for other programs and processes to overwrite. So it's not zeroed out or anything. If you really want to keep your data secure, you might want to run programs to zero out data after deleting files. But it will allow other programs to start overwriting the contents or the region of memory where that file was originally stored. Okay, so let's go on to the next question. What Unix standard command can I use to view help for shell commands that are programs? So this is a big distinction. For programs, you would use man. So I can, and also for other things as well. So if I type in man and then cat, you can see the help pages, the manual pages for the cat command. And if I say man, you can actually see the different sections of the manual pages here. So section 1 is for executable programs and shell commands. Section 2 is for system calls, etc. But we don't have a manual page section for shell built-ins. And you can check if something is a shell built-in, going on to the next question here. What shell built-in can I use to check whether a shell command is a program or a shell built-in? You can use the type built-in, type-a specifically to see all types of a command. So if I say type-a echo, you can see that echo is a shell built-in. It's also defined as a program. But since the shell built-in comes first, my shell, bash, will default to using the shell built-in of echo. So if I wanted to get help for a shell built-in, let me actually show another command that maybe is a better example, cd. cd is only a shell built-in. So if I were to try and run man for cd, I would get no output. But if I wanted to learn more about the cd command, let's go on to the next question here. What shell built-in can I use to view help for other shell built-ins? I would use the help shell built-in. So help cd, and this would actually print out a big help message here for me. I'll zoom out a little bit so you can see it all. A big help message telling me all about the cd command and the different flags I can pass to it and whatnot. So man for programs like cat, and help for shell built-ins like cd. And if a program exists as both a shell command and a shell built-in, so for instance, echo, I can run man for echo. I can also run help for echo, and both would work. You can see. And if I wanted to overwrite, so again, if I went typed in type dash a and to view echo here, you can see by default my shell uses the built-in version of echo. If I wanted to explicitly run the program of echo, I would just have to pass the specific path to echo here. And then I could actually run echo hello, and that would actually use the binary echo. I could also use the command shell built-in to specify that I want to use the program of echo instead of the built-in version of echo. I could also use the built-in command to view the built-in version of echo instead. All right, so maybe a bit too much detail for this question's answer, but I think it'll only help you to know all these little things, so you can make sure you are able to get help, the appropriate help for whatever commands you are using. Okay, so now for the next section, processes and advanced information about processes. How do you redirect standard out and in of a bash command to a file? For instance, if I want to redirect grep's output or input to the file grep.txt, what do I type? Okay, so let's do the output first. So if I were to say grep, let's say grep main, grep for main in read.c here, we can see the output. I would use the greater than symbol to redirect my output to a file, which we'll call grep.txt. And now if I cat out the contents of that file, you can see that it did in fact print the text main. Now what I can also do is grep for main and then redirect its input. So I could say redirect the input of grep to the file grep.txt by just switching that redirect symbol around. So now it's a less than symbol. And now if I do this, it feeds grep.txt's contents to grep's standard in, and then it searches for the text main. This is kind of a superfluous example because you can just pass a file name directly to grep, but I think you get the idea of being able to redirect input into a program. How do you redirect standard out from one command to another command standard in? For instance, if I want to count the results of find with WC, what do I type? So there's two ways to do this. One of them is using process substitution, but I'm not going to quiz you on that because it's more esoteric and not as usually useful as the second option here, which is going to be pipes. So we're going to be talking about pipes. So for instance, if I wanted to cat out the contents of read and then count the number of bytes, words, and lines in that output with WC, I would use a vertical bar right here between the two commands. And then if I run this, you can see I get the output here. So again, just running cat gives me the output here. The vertical bar lets me pipe the output of cat to WC. And to see visualizations of all this, I would recommend going over the previous lecture videos for diagrams and more detailed explanations. Okay, build automation. I'm going to go into this build automation directory I prepared for this section. What does the target recipe prerequisite of a makefile do? Okay, so a target tells you what you want to build, the recipe tells you how to build it, and the prerequisite tells you what you need in order to execute the recipe to build the target. And now let's see a demonstration of all this. So write a makefile that will create a program called hello from two sources, main.c and hello.c. So let's look in this current directory. We have three files here, hello.c, hello.h, and main.c. I'm going to run cat on all these files in sequence so we can see their contents. And I'm using cat and not, actually let me use head. The reason I want to use head here is because it'll print these little headers between the files. That's not what head normally does, or it's not why it's called head. It's called head because it prints the first 10 lines of each file. But it also, in this case, these files are small, so it doesn't matter. And it also prints these headers between each file. So for the file main.c, we have just we're including this hello.h file and then calling this function called hello. In hello.h, we're just declaring that function hello as a function which returns nothing and accepts no arguments. And then in hello.c, we are defining that function hello to just print the text hello world. So I could actually compile this from the command line directly, just saying hello gcc-o hello to call my binary hello. And then I'm going to compile hello.c and main.c. And if I run this, you can see it works, and I can run that binary hello to print the text hello world. I'm going to delete that binary now. So let's make a makefile to automate this process for us. So let's create the makefile, and we're going to create a rule now. We're going to call it hello. So to build the target hello, we need main.c, and we need hello.c. And note that in makefiles, you cannot use spaces, you must use tabs. Otherwise, you will get an error. Now to build this target here, hello, we're going to say gcc -o, -o, hello.c, or main.c, I should say hello.c. And now if I run make, you can see it actually runs perfectly well, because by default make will run the first command in its file here. So the first rule defined here is hello, so we're just going to run hello by running make. So I can run make and it'll run it. If I run make again, and we'll say hello is up to date, make can detect that no changes were made to the files that the hello binary depends on, hello.c and main.c, and so make does not bother remaking hello, and I can run that binary and it works like expected. Now, there's some additions here we can make. For one, we can use the make special variable $circumflex. This character is called a circumflex. And what that will do is expand to all the prerequisites. So if I run this, you can actually see it works. Let me remove that hello file. You can see it works just like before. Another thing we can do here is use the special variable $@. This is given to us by make, and this will expand to the target's to the current recipe's target, I should say, the current rule's target. So again, if I were to remove hello and then run make, you can see it actually compiles just before as well. So not really necessary for the exam perhaps, but I think it's good to know these little shortcuts because it lets you write generalizable template make files this way. Okay, now let's go on to the next question. By convention, what does the clean target do? So the clean target by convention, and this kind of goes into the next question as well, so I'll answer both of these at once. It removes binaries. It removes generated code from a project. Usually you have no dependencies for clean. All it does is remove the file, the dependency, or not dependency, the target of the project. So in this case, hello. Now if I run make clean, it will remove that hello file. One thing to note is that if I run it twice, we'll get an error message because hello does not exist. So how can we fix this? How can we make hello, rm not emit an error message even if the file we're trying to remove does not exist? Well, if you've been paying attention, then you might remember that we saw this earlier. You would use the -f flag. So now if I run make clean, we don't get an error message no matter how many times I run it. One more thing to note about clean is that because this is the name of a command we're trying to run and not a file, we want to add it to the .phony list of commands up here. So clean. And let's see what happens if we don't do this. So I'm going to comment this line out. If we don't say that clean is a phony command and we try to run make clean, it'll work. But if we create a file here called clean and then try to run make clean, make will tell us clean is up to date. Because remember, the structure of make rules by default is target, prereqs, and then recipe. So if we don't tell make that clean is actually the name of a command by putting it on the phony list, make will actually think that clean is the name of a file we're trying to generate. So if it sees that the clean file exists, it will actually just not run. So let's fix this by removing our comment here, making this part of our make file. And now if I run make clean, it will actually still run, even if that clean file exists, which I'll remove now. Okay, so much for build automation. Let's go on to the next section. Version control. Okay, what git command stages a new file? So the command to stage a file, I'm going to scroll down here now to some other content I've prepared. Let's say we have a git repo whose working tree contains just the file hello.c. If you wanted to move that file to the staging area, what we would do is use the command git add. So I'm going to draw this here with this arrow. Okay, that should be nice and pretty. And we'll say here, git add. You know what, I'll make this full screen since we're not using the terminal right now. And so if we ran git add to add hello.c to the staging area, you can conceptually view it like this. What git command creates a log of the change to the staged file to the local repository? That would be git commit. So I can select these two and duplicate this. This would commit the file to the local repository. What git command commits from the local repository to the remote? That would be git push. So I can say git push here. And now that would put it over here. And actually what I should represent that as duplicating, because we're not moving the file from our local repository. We're not removing it. We're just really duplicating and pushing these commits to the remote. And finally, what git command copies commits from the remote repository to the local repository? So assuming your local repository already exists, what you would use is the command, let me draw this here. Actually, what I'll do is just draw a new arrow. Assuming that your local repo already exists and you're pulling from a remote, you would use git pull. Now, if this repo didn't already exist, let's say it didn't exist at all, then what you would use is git clone instead. And that would create a copy of your remote. Oops. As your local repo. And I'm not going to draw the lines here, but the staging working directory, the working tree, I should say, the staging tree, staging area, and the commit local repo would still exist here as well. Those different sections. Okay. So next, let's look at file syscalls. Okay, so now we're going to get onto syscalls. So we're going to be, I think, done with these slides now. So I'm going to close this and go back to the terminal here. Using the open syscall, use the open syscall to open a path given in the string char star file path variable. Okay, so let's look at open. I've actually prepared a file for this, so open.c. So we're going to store the text open.c. We're actually going to store the name of this file itself in this string here. We're going to open this file for reading using the open syscall. This expects a file path and a flag, or flags, specifying how we want to open the file. We're going to open it just for reading, so we're going to pass the oReadOnly option here, and store the result in the ft variable. This is going to store the file descriptor of the resulting file that we opened. If it's -1, then we failed to open the file, so we print an error message using p-error, and then exit with exit failure. And again, if you want to view the man pages for any of these commands, you can press 2 in Vim and then capital K to go to the manual pages for the syscall for open. If you forget to press 2 first, then that will open the binary, the manual pages for the binary open, which is not what we want. So we're going to press 2 and then capital K to open the manual pages for the open syscall, not the open binary. So after opening this file, we're going to just close it, and that's it. So we're not going to do anything with this file. We're just opening it and then closing it. So if we run this, so make open.c, or make open, and then run it, nothing happens because we didn't print anything. We just open and close the file. That's it. But if I were to check the return status of this program with echo $? You can see it's 0, which means it was a success. Number 2, how do you check for and terminate the program on error with opening a file? Well, we saw this in the open.c file. You just check if the return value of the syscall is -1, and if it is, then you p-error and then exit. And this isn't always going to be -1. Most syscalls return -1 in error. Some return null. I think some return null. Maybe it might be library calls I'm thinking of. But if you ever want to check, you can just hold Shift and press K, or in this case 2K. Search for return value, all caps in the man pages. So the way you search is by pressing / and then typing in the search keyword, search term. And it will tell you what is returned on error. So in this case, -1. Okay, so let's go on to the next question. Using the read syscall, so man to read, not fopen, you already have an open file with a file descriptor stored in fd. Read the first 200 bytes of the file and print it to standard out. So how would we do this? Well, I have another file here called read.c. And here we are again opening the file open.c, but we're also creating a buffer with 200 characters in length, and then a count of 200 as well, so we have the same length stored as our buffer. Then we're creating a variable here to store the number of bytes we've read from the buffer. We'll use that later. And then opening that file in read-only mode as before, storing it in the file descriptor in this variable fd. So if we have -1 as a result, of course we exit early. Otherwise, we use the read syscall to read from the file descriptor fd, store the results in the buffer buff that we declared up here, and we're reading count number of bytes. So in this case, 200 bytes. So that's the same length as buff. That was on purpose. And we store the number of bytes read in this variable bytes read. So read by default, if I go here and look for, to capital K, return value. On success, the number of bytes read is returned. So this should tell us how many bytes were read from the file. We can check for errors, of course, like normal, checking for -1. And then we just print out one by one. We're just iterating through this contents of the buffer, printing out all the bytes read one by one with this printf line down here. Then we close the file and then return success. So let's try making this. So make read, and then if we run this, you can see it actually prints the first 200 bytes of the file read.c. Okay, so next, let's look at this one here. What's this call can you use to find the size and number of hard links of a file? That's going to be the stat syscall. So here, we're storing, again, the file open.c. We're creating a stat struct we're going to call sb. So this is part of how we call the stat syscall. It expects you to pass a file path. There is a variant which accepts file descriptors. We're going to pass a file path. And the second argument is the address of this stat struct, which is going to have its fields populated with the results of stat. So if I do to stat, you can see more information about how stat works. These functions return information about a file and the buffer pointed to by statbuff. And I could actually say 3stat to view the type information about that stat struct and what fields it has. And you can see it has two fields here, size, st size, and st and link, which are exactly what we want here, the size and number of hard links. Okay, so one more thing, let me actually run this then. So we can see here we print the size field of the file, and we also print the nlink field of this file as well. So let me try running this. So make stat. So I have a make file prepared for building all these files here, all these programs. So I'll run the stat program, and you can see it actually prints the size of the read.c file and number of hard links. And if I ran the stat binary here, this is the system-wide stat binary, on read.c, you should see, it must be the wrong one, open.c, I'm sorry. Yeah, and now if I run /stat on this program, you can see the file contents match. So according to the stat binary or program here, open.c has a size of 360 and has one hard link to it, and so does the /stat program. This returns the same thing about open.c. So this seems to be correct. Now, one thing to note is that hard links to a file have different inode numbers. Different inode numbers, or no, they share the inode number, I'm sorry. So if I were to create a hard link with the ln command here, ln, I'll just say stat2, and I'll do this for the, or maybe open.c-2, or .lnk to open.c. This would create a hard link. Oops. I think I have to do this in reverse. Open.c, there we go. So now if I do ls, you can see I've created a link to open here. It should be somewhere here. Open.c.link. I can say stat open.c.lnk, and it will actually say that it's a hard link. And hard links have different inode numbers. So if I do ls-i1, you can see that open here, open.c and open.c.link, oh, I'm sorry, same inode numbers. Yeah, same inode numbers, that makes sense. So what this means is that if I delete all the hard links to a file, that file will effectively disappear. It's not until I've deleted all hard links to a file will it disappear. On the other hand, if I were to create a soft link, so I'll delete this link that I've created with the -s flag to ln, so ln-s open.c, open.c.lnk, and then run this command to view the inode numbers of all these files here. you can see that open.c.lnk actually has a different inode number from open.c. So if I were to remove open.c.lnk, that would not actually affect the contents of open.c or its file. It would not be deleted. But if you delete all the hard links to a file, that file will be gone. And hard links share inode numbers with each other. Okay, what syscall can you use to find the name of a file? So let me actually check this here. I have this file here, program here to show it. This is sort of a trick question. We're not going to use syscalls to find the names of files. We're going to use a library call. You could use a syscall, but we're going to use the library calls here. With opendir, redirection, and closedir are the three we use. Redirection specifically gives you the file names. So this is actually going to sort of play into the second question here. What we're going to do is open the current directory. So with this opendir library call, open the current directory, save the result in this dirp variable, and then declare this dirent pointer, this struct dirent pointer, we're calling dirent. If dirp is equal to null, that means opendir failed, so we exit early. Otherwise, we set error node to 0. This is how we check for errors with redir, so we have to set error node to 0 first. And we call redir repeatedly until it equals null, storing the result in dirent, and each time we're going to print the dname field of that dirent struct. And afterwards we can check if 0 is equal to errno, and if it's not, then we know there was an error occurred, and then we can exit early. And then otherwise we close the directory pointer with closedir, and then exit success. So what this should do is just print all the files in the current directory. So I can run make dirs and then run this file, this program, and you can see we actually have all the directories, all the files in the current directory printed. So now for this next question, write a code snippet that prints all files in a given directory except do not print the dot and dot dot slash names. What we would need to do is include the string.h header. So I'm going to sort these actually. Okay. And we can just check inside this while loop if string comp dirent dname dot. So if 0 is not equal to string comp, so string comp returns 0 and the two strings are equal. So we'll say if 0 is not equal to string comp dname and dot. And so I'm going to have another condition here. 0 is not equal to string comp dirent dname dot dot. Only if both these conditions are met will we print the name of the current file. And I think I might have missed a closing parentheses there. Yep, here we go. Now if I run this and try to run this, you can see we have the do not print dot and dot dot slash. We omit those from the output. All right, final section. Write code that creates a new process where the original process writes parent and the new process writes child, both to standard out. All right, so I already have a file prepared for this one as well. So we can say fork.c. This file has the contents. So we're calling fork inside of a switch condition here. So we're doing a switch fork idiom. If it's -1, that means we have an error. If fork returns 0, that means we are into the child process. So we'll printf child. And because we're in the child process, we'll want to exit using the _exit syscall. The thing is, this will avoid doing any cleanup tasks that should be left for the parent to do. So it's good coding practice to use _exit instead of regular exit inside the child. But because we're using _exit, this does not guarantee that these standard I/O buffers will be flushed, which means you have to flush them ourselves manually, and we do that here on this line. This just ensures that the output child reaches the terminal. If we don't leave this line here, if we comment this line out or we just delete it, we may not even see the output from this child process printed to the terminal. So this is just to ensure that we see it. On the parent process, we're going to wait for the child to finish, and then we're going to print parent and then exit success. So if I were to make this and then run it, you can see we see child and parent. All right, I guess they're not numbered, but the next question here. Write code that replaces the current processes running program with the stat_ls command. So this is going to be simple with the exec syscall. So here we're using exec LP. There are many different variants of exec. The LP variant is what I'm using here. What L stands for is list, which means we can pass the program name and its arguments as a list and then end the arguments list with the null value. And what the P stands for is path, which means we don't have to pass the full path to the program. I don't need to pass in user bin ls here to call ls. By using the P suffix version of exec, when we call exec will search our path variable for any program binaries which are named after what we've passed as our program name here. And because user bin is on our path, so I can actually show this, if I echo out my path variable, then let's see here. I'll pipe this to grep for /user/bin. You can see user bin is in fact on my path. And so in user bin, the ls command exists. And so that's how this call to exec in exec.c is able to find the ls command. I'm going to comment this line out. And if I run this, so make exec, and then run exec, it will just run ls. Now if I were to comment this line out here, and leave this line uncommented, so we're going to run stat, passing the file exec.c, so this file that we currently have open, to stat, and then run this. Let me make it first, rebuild it. You see it actually runs the stat command on exec. And one thing to note is that because exec totally replaces the current running process with a different program, then that means that all the rest of this file will not be executed if exec succeeds. So this call to stat will not even be run if ls succeeds here. So if I actually run this again, make exec, and then run exec, you can see it actually goes back to just printing ls. It doesn't even run the stat command. So really what you'll probably want to do, instead of having another call to exec here, you'll probably want to have just p error immediately after exec if it doesn't succeed. In fact, this should not even be exit success. This should just be exit failure, because if we manage to reach this point in our program, that means exec didn't work, which is of course an error. So we'll just leave this here like this instead. And we'll remake it just to be safe. Okay. Next question, write code that uses Unix standard syscalls to create a new process that runs the ls command. So here we're just going to combine the previous two questions answers. So we're going to say fork exec here. Here we're just calling fork like we saw in the previous fork example. And in the child process, we're going to run exec lp to run ls. And in the parent, we actually we just wait for the child to finish running. We don't have to worry about flushing standard out here because we're creating a child process, or we're replacing the child process with a different command. And when that command finishes running, it has its own exit function that will be executed that will close its file descriptors for it. So it will close and flush standard out for the child once we call exec lp. So all that basically means is that I can build this program and then run it. So fork exec, and it will just run ls as before. The only difference is that we have two processes I should say doing this, a parent process and a child process. Okay, write a program that opens a pipe and reads to and writes from it. So pipe.c. So the way pipes work is when you call the pipe syscall to open a pipe, you have to pass in a array variable, integer array variable of size 2, and the index 1 of the array variable will be set to the right end of the pipe, and index 0 will be set to the read end of the pipe. So let's go from the top and see this. So we're creating a message here, storing the contents hello in it. We're getting the length of that message in this variable count, storing in this variable count. We're creating a buffer for storing the results of the pipe, and then another bytes read variable here to store the number of bytes that we actually read from the pipe. So first we're going to open the pipe and exit on failure. Then we're going to write to the right end of the pipe. We're going to write the message and this many bytes of the message, which should just be the length of the message itself, since we use string length to get the length of the message there. Then we're going to close the right end of the pipe because we're done using it. We've already written to it. We no longer need it. Then we're going to read from the read end of the pipe, store the results in this buff variable, and we're reading count bytes, which again is just the length of the message. So it should be fine to do that. Oops, let me go back. Okay, oops, right here, okay. Then we're closing the read end of the pipe because we no longer need it. And then we're finally printing out every character in the buffer in this for loop, and then finally printing a new line character so it looks nice in the terminal window. So let's try running this. Make pipe, and then /pipe, and that will say hello. One thing to note is that you might not like how we have to pass in these magic numbers here. Pipe FD1, it might be kind of hard to remember. A trick I would recommend doing is just creating an enum called read and then write. So an anonymous enum with the values, the members, read and write, and they can just be equal to 0 and 1. And now whenever you want to refer to the right end of the pipe, you just can pass in this symbolic constant, this compile time constant, I should say, write or read. And this will actually make your code a little bit easier to read because you can know which end of the pipe you're referring to without having to just remember that 1 is the write end and 0 is the read end. So if I run this, make pipe, and then run this, you can see it works just as before, but it's a bit easier to read the code. Okay, last but not least, write a program that redirects the standard output to a file called output.txt. So let's look at this. We're going to use the dupe2 syscall to achieve this. So we're opening a file, output.txt. We're opening it for writing only, and if it doesn't exist, we're going to create it. If it does exist, we're going to truncate it, so set its size to 0 before we write. So we're going to overwrite whatever contents are in the file, effectively like deleting and then writing to it. And we're creating it with these permissions if it does not exist. What this is going to set is read write for users, and read for groups, and read for others. That's what these permission bits will specify. If we fail, then we close early, exit early with an error. If we succeed, then we're going to try and call dupe2. What this will do is first close the standard out file descriptor. Then it's going to reopen that file descriptor, pointing to the same file description in the file system table that the fd file descriptor was pointing to. So after this call to dupe2, right here, standard out should be redirected to fd. And now that we've successfully completed the redirect, assuming we don't fail here, then we'll close the file descriptor because we've finished doing the redirect. Standard out already now refers to the file output.txt, so we no longer need the file descriptor. And then we're just going to print hello from dupe2.c with a new line character at the end, and then exit with success. So we run this and it works. We shouldn't see anything to standard out. So let me run make dupe2 and then run this. And we see nothing to standard out, so it might have worked. And let's count out the contents of that file output.txt, and you'll see it actually says hello from dupe2.c. So it seems to have worked. All right, so I'm going to run make clean to erase all my binaries here. And I'm going to bid you all adieu and good luck on the midterm. I will see you all on March 3rd.